Hi everybody, today we're going to talk about financial engineering and risk management, introduction to martingales. Let's go. A random process xn, 0n to infinity, is a martingale with respect to the information filtration fn and probability distribution p if the expectation of xn is less than infinity for all n greater than or equal to 0, and the expectation of xn n plus 1 given fn, the filtration fn, at time n is equal to xn for all n m greater than or equal to 0. So what does the first condition say? The first condition says that the expectation of xn is not infinite. So there can be times when the norm of a random variable or an element in an LP space is infinite, so we don't want that. I think it can go up to infinity, but it shouldn't be infinite. Like, it shouldn't be straight up infinity. This E of P, this is a probability measure, which is not something I know a lot about. So let's go to the second condition. So this is saying that the expectation of xn m plus 1, so the random variable xn x at a time in the future, n plus m, given fn is supposed to represent a filtration, so it's all the information we have available up to time n is equal to xn. So this is a fair game, which means that if we are at time n, the expectation of the value of x of this of this random variable xn n plus 1 is the same as xn. So we just based off the information now, the expectation is not supposed to change. So in mathematical terms, a filtration is I think it's the sigma algebra of all random variables that exist up to time n, which includes x1, x2, all the way to xn, but includes all the information. So if there's any more information, any other random variables, then it includes that. Okay. Martingales are used to model fair games and have a rich history in the modeling of gambling problems. We define a sub-martingale by replacing condition number 2 with this, and a super-martingale by replacing condition number 2 with that. A martingale is both a sub-martingale and a super-martingale. So this is greater than or equal to, so this would, a sub-martingale would mean that the expectation is bigger than or equal to, and super-martingale means expectation is less than or equal to. Okay. Constructing a martingale from a random walk. Let Sn is equal to infinite sum of xi be a random walk where the xi's are independently distributed with mean mu. So it's a random walk, so we start at position 0, and on average we're going to walk mu, but I'm sure surely this is not an infinite jump. We could go here or here, but on average we're going to go by mu, which might be positive or negative or 0. And so that Sn is the sum of all these xi's. So the first x1 we're going to go 1, and the next x2 we're going to start here and go somewhere else, maybe backwards or forwards or whatever. And then Sn is going to be where we end up after xi. Let Mn is Sn minus n mu, then Mn is a martingale because of this proof. So what is Mn supposed to represent? It's supposed to represent where we end up minus this n mu. So the idea is that after every single step, on average, we move mu. So this is like a sort of balancing factor where we have Sn minus n mu, and hopefully this is, not, it's supposed to be kind of 0, I think, if that makes sense. Yeah, I wonder if it actually is 0, the expectation. Anyway, so yeah, so we took this definition here and we inserted it here, and then this is just a constant, so we took it out, and then we know the information in the, this is En better, according to his writing, better to say Fn, and according to Fn we know what the value of all the xi is, so we just moved it out of here and we just end up with this. then the expectation of this is not dependent on the fn at all. It's independent because the xi's are identically independently distributed. That's why this becomes mu here, and so we end up with mn, right, which is just this plus, and then this cancels out, and we end up with just mn. So Sn minus mu n mu, right? Okay. A martingale betting strategy. Let x1, x2 be identically independently distributed random variables with probability xi equals 1 is probability xi equals minus 1 is equal to 1/2. So we are flipping a coin, and with probability 1/2, we get a payout of 1, and with probability 1/2, we get a payout of minus 1. And so what we're going to do is we're going to double our bet every single time we play it. So we're going to start out with $0, and then we're going to bet $1, and we might potentially end up after one turn at minus 1 or at 1. So if we end up at 1, this is it. We stop playing. But if we are at minus 1, then we're going to play again, and we're going to double our bet. So now we're going to go potentially to minus 3, or if we win, we jump to 1, and then again we stop playing. And now that we're at minus 3, we're going to bet how much? How much do we bet? 4? Yeah, so we double. So 1, 2, 4, 8. That's our bet keeps doubling. If we lose, we go to minus 7. If we win, we go to 1, and then we stop. So that's the idea. So we might potentially be losing an infinite amount of money, but every coin flip, we have a chance to get back up to 1 and make profit, if that makes sense. First, note the size of the bet play is 2n minus 1. That's what I was talking about. Let Wn denote total winnings after n coin tosses, assuming W0 equals 0, then Wn is a martingale. So it's supposedly a fair game. Okay. A martingale, it's a fair game even though we're infinitely likely to end up with profit, which is kind of weird. To see this, first note that Wn is either 1 or minus 2 to the n plus 1 for all n. Why? I already went over that. Suppose we win for the first time on nth bet, then Wn is that. If we have not yet won after n bets, then Wn is that. To show Wn as a martingale, we only need to show this. This follows by iterated expectation. So the proof that he gave was the following. The expectation of Wn plus 2 given Wn is just equal to the expectation of Wn plus 2 given Wn plus 1. And outside of this, given Wn. So we know what this is. If we know this, we know this, and then we know that. Yes. So basically, we can replace this. Yes, we can, inside this expectation, we can replace Wn plus 2 with, crap, I will maybe try to explain that later. Okay, there are two cases to consider. Wn equals 1, then P of Wn plus 1 is 1. So yeah, if we're already at 1, then that's our like stopping point. So we just do nothing, and that's why the expectation is just we're always just going to stop, and that's equal to Wn. So, but then if Wn is minus 2 to the n plus 1, we're going to bet again, and then we might win and go back up to 1 with probability 1/2, or we might lose further with probability 1/2. And then we calculate this expectation here, and we end up with Wn, and therefore it's a martingale because it's a fair game. Okay, Poli's urn. This is the last example. Consider an urn which contains red balls and green balls. Initially, there's just one green ball and one red ball. So, so here's an urn, and then here's a. We'll be fancy and use different color. So here's a red ball, and then here's a green ball. We start out with 1 and 1. So in the first turn, we pick out a ball from here, and if it's a red ball, we put it back in, and we add another red ball. And then if it's a green ball, we put in. So basically, after one turn, there's either, depending on what we picked out, there's either an extra red or an extra green. So the number of balls will keep increasing in this urn. So that's why we can't just say like a martingale on the number of red balls. The martingale will be on the number of red balls divided by n plus 2, because it's supposed to be increasing every single turn. by either 1 or 0. That's like the number of red balls. And so then we have this n plus 2. So show, I think he did the calculation here that if xn equals k, with probability 1/2, we pick out a green ball and k does not go up. Or, sorry, it's like, so basically, if xn equals k, from this you can calculate how many red balls are in there, and then this is the probability that you pick out a red ball, which is why k plus 1. The martingales, again, it's the number of red balls. And then this is the number of green balls, and n plus 2 minus k, and then there's n plus 2 balls in here because we started out with 2. And with this probability, we pick out a green ball, and that's why xn plus 1 equal k. Okay, show that it's a martingale. So I already did some scratch work here, but I'm going to do it again in a different color here. So expectation of mn plus 1 given the filtration of n. So mn plus, this is equal to xn plus 1 over n plus 3. Again, this the number of balls keeps increasing, which is why we have this factor down here, n plus 3. So then, according to my work here, I just plugged in the expectation is equal to either we pick in the time at time n, either we picked out a red ball and we ended up with k plus 1, or we picked out a green ball and we ended up with k. And then we have this factor n plus 3 here from this. So then after a little bit of manipulation, forgot the n plus 3 here, then you see we can just do that. Then that cancels out. We end up with k over n plus 2, which is exactly the value of, so this is equal to mn, right, from here, xn plus n plus 2, given that, so I forgot to mention here that the condition is that I'm just replacing xn with k. Well, we know that the value of xn from all the information up to time n is k, right? Yes? Okay, good. Oh, crap. What happened here with my... okay, I'm gonna... There you go. Okay, yeah, so I just, I didn't get the work done here, but this is this is the proof for the red ball and the red ball and the green balls in the urn. Okay, great. Thank you. See you next time.